So let us see different common probability distributions. We already know that we have discrete distributions and we have continuous distributions. So accordingly, we have different types of distributions. Under discrete distributions, we have Bernoulli distribution, we have binomial distribution, multinomial, and Poisson. There are many, but these are very commonly used or very popular distribution functions. Similarly, in continuous distribution, we have uniform, beta, gamma, and Gaussian is one very important. We have so many such kind of distributions. Before we go, I think I will just quickly repeat what is discrete and what is continuous. In discrete, the values are finite and limited. They are countable. Discrete means when you do an experiment, if you quickly recall what we have seen, when you do an experiment, it has some outcome. Okay, this outcome, like this, I'll be doing experiment for n number of times. So we'll have n number of outcomes, and all those outcomes are random because we do not know what will come to us. When I do experiment 1, I do not know what could be the outputs. Same experiment, if I repeat second time, I may get another outcome. So if I repeat the same experiment n number of times, I may get different outcomes in each experiment. Since this outcome is random, we store this value in a variable. This is called random variable because the value which is being stored is random. It is coming always different. Now, that value which is coming from an experiment, the outcome which is coming from experiment, from this experiment, if it is limited or finite and countable, if it is limited and countable, we say that this particular random variable is a discrete random variable. Like for example, marks in an MCQ exam, 10 marks, 10 MCQs are there in that exam. One test is there and each one carries 1 mark. So the values of this random variable or the outcome of this experiment will be from 0 to 10. And it is limited, it is finite, everybody can count. We all know how many marks students get, either 0 or 1 or 2 or so on, or 9 or 10. This is finite. That's why finite and countable, that is discrete. Same experiment, if I repeat, and I may get random outputs from this, right? I may get random outputs from this when those outputs are infinite. When the output are infinite and uncountable. Infinite and uncountable. In that case, we call such kind of random variable as continuous random variable. Continuous random variable. Why? Because example can be weight. Weight of students. For example, if I take, right? In this case, weight, it is not finite. Weight can be anything. Maybe it is from 40 to 120, 130, we do not know. And in that we have so many, somebody is 50, 56.1, 73.2, 88.1. We have n number of values. We cannot count how many values are there. So the random variables, the experiments which give such kind of outcomes, and if such kind of outcomes are stored in such random variable, we call that random variable as continuous random variable. Okay, so the distribution, what is probability distribution? What is probability distribution? When you generate a list of probability, list of the outcome, the random variable, outcome and its probability. When you form a list, when you club together the outcome and its probability, this is called a probability distribution. Okay, this is called a probability distribution. For example, if I roll a die, I may get the values as 1, 2, 3, 4, 5, 6. And what is the probability of getting 1? It is 1 by 6. Similarly, 1 by 6. Like this, if we group together, if we have the values of the outcomes of that random variable and the probability of getting this particular outcome together, if you club it, and store have it with you, then this kind of data is called as this forms a probability distribution. So it is here, it is represented as p of x in discrete, whereas in continuous it is represented as f of x. It is represented as f of x. So we have seen that in discrete, the probability distributions, their value is something like this: p of x greater than or equal to 0 and p of x less than or equal to 1. So we write it something like this: x equal to x equal to small x. The discrete probability distributions are represented like this: p of capital X equal to small x. Whereas in continuous probability distribution, we write the function f of x and we don't give it as a simple in a single value. We give it as a value like this: a less than or equal to x less than or equal to b. We give in a range because it is infinite and I cannot specify its value. So we give it in a range like this. So when for all these continuous probability distributions, values will be in this range. For all the discrete probability distributions, values can be written like this. I can use it like this, or I can say it in this way. Maybe I can say p of x is 0.3. I can give it directly a value, right? So that is about discrete and continuous probability distributions. Under discrete, we have few. Under discrete, we have Bernoulli, binomial, antinomial, Poisson, and so on. And under continuous, we have uniform, Gaussian, and many other exist. So let's see few of them, understand how and where they are used. Right. So binomial probability distribution. The first one we are seeing, trying to see the discrete distributions. In that, the first one is we will see binomial distribution first. So binomial probability distribution. What is this? So a fixed number of observations. That's what discrete means: fixed number of observations. Okay. So example: 15 tosses of a coin, 20 patients, 100 people surveyed. So such kind of examples. Okay. A binary random variable. It's a binary random variable because it gives only two output, either yes or no. Okay. Because you see here, 15 tosses of a coin, I may get only a head or I may get a tail. Okay, so the random variable which is used in binomial probability distribution is a binary random variable. Okay, head or tail in each toss, defective or not, light bulb case. So generally it is called as success and failure. So problems, when you have data with you, problems where you want to see, you want to talk only about the two cases, yes or no cases, then we apply binomial probability distribution. So success is represented as P, failure is 1 minus P. Success is P and failure is 1 minus P. Okay, so constant probability for each observation because it's fixed. We know each observation will get constant output. Like probability of getting a tail is same as getting a coin. Same each time we toss the coin because I toss a coin. How many times will I get tail? It's always 1 by 2. N number of times you do. How many times? The probability of getting a tail is 1 by 2 only. It does not changes. So see example here. Example of 5 coin tosses. What's the probability that you flip exactly 3 heads in 5 coin tosses? I want to get 3 heads. Right. So if you see the outcome here, 3 heads means I can get it something like this: first time tail, next 3 times head, then tail, then 3 heads, 2 tails. So in these different fashions, I am doing it, I am tossing it. So I may get these different combinations. Now, what is the probability of getting that? Getting tail is 2. So 1 by 2 whole square into 1 by 2 whole cube. Why? Cube because 3 times head. That way you see the outcome is fixed always. For these 10 arrangements, it is nothing but 1 power half cube into half square, 1 by half square. Why? We are talking about getting exactly 3 heads. So the probability of each unique outcome, they all are equal, right? Why I made 10 things? Because using this combination, 5 ways to arrange 3 heads. Ways to arrange 3 heads in 5 trails. So I am doing 5 times I am tossing it. So how many ways can I get head? So 10 times. So with that I got it. So it is clear why I made this 10, because it is 5C3. In 5 tosses, I have to get 3 heads, but it can be in different locations. First time only I can get a head, second time I may get a head. So that way different combinations exist. But the probability of all the cases you see, it is fixed like this. So getting 3 heads and 2 tails, that's it, right? Because I'm talking about 3 heads exactly. So the remaining will be definitely 2 heads, 2 tails. So 5C3 into probability of getting heads per cube into probability of getting tails per square. So here you can do that thing. When you get heads, my target was to get head. So success P is 1 by 3. So other term will be, 1 by 2. P of getting 3 heads, probability of getting heads is 1 by 2. That is P. 1 minus P will be again 1 by 2 only. So 1 by 2. So if you multiply that, you get something like this. So the probability of getting 3 heads when you toss a coin 5 times is 31.25%. Okay. So we use binomial distribution in such cases. Let's quickly summarize. When you have some fixed number of observations, we go for binomial distribution. Okay, fixed number of observations like this. See here, question I have given 5 coin tosses. They have told only 5 coin tosses and exactly 3 heads I am talking about. Next one is Bernoulli distribution. Okay, a little modification to what we have seen in binomial. In binomial, we said that we talk about success and failure, only 2 cases, success case and failure case. Same thing here. If there is only one trail, okay, here it is fixed number of trail. If you see, here we are having some fixed number of trails, 5 coin tosses, which is fixed one. But here, if there is only one trial with the probability of success P, probability of failure 1 minus P, this is Bernoulli. So we don't do it the experiment multiple times. We do it only one time. In that case, we apply Bernoulli distribution. So see here what we are writing, 1C1, that is 1 always, success into 1 minus P. Okay, so it's always P. So probability of getting 1 and 0, it is P and 1 minus P. Very simple Bernoulli distribution. If the experiment is done only one time. Now tell same example of, I don't think we have taken here, same example of coin toss. I am saying, let's modify this question here. Take an example of one coin toss. One coin toss. What is the probability that you get exactly one head in one coin tosses? What is the probability of getting one head in one toss? It is 1 by 2. And getting a tail is 1 minus 1 by 2. Same again, 1 by 2. Okay, so this is the Bernoulli. It's a special case of binomial. In binomial, we have fixed number of trials. Trials means experiment, trying it multiple times. If that particular trials is only one, then we say it is a Bernoulli distribution. So we represent it like this. Probability of success is P and probability of failure is 1 minus P. Third one, multinomial distribution. What is this? Multinomial. Binomial, here we have seen in binomial distribution that the outcome is always 2. See here, binary random variable. Binomial probability distribution, the random variable is a binary random variable. It means when I am doing an experiment, I get outcome. This outcome is not random. It is random, but it is only 2. It has only 2 output, either a head or a tail. This is binomial. Okay. Multinomial means here we get multiple outcomes, but fixed. Let's see that. Multinomial. It's a generalization of binomial. It is used where there are more than 2 possible outcomes. More than 2 possible outcomes. Multinomial distribution. So I do an experiment, I get an outcome. This outcome, it has fixed things, but more than 2. Then we go for multinomial distribution. So instead of partitioning n trials into 2 outcomes, here we partition the n trials into 3 or more outcomes. So P1, P2, P3, so on. You see here how you write here. Since there we were writing NCR into P power N into 1 minus P whole power N minus R. This we were doing there. 5 times P power R and P power R 1 minus P into N minus R. We were doing that for binomial or Bernoulli also, same thing we have followed it. But everywhere it is 1 in Bernoulli. But here it is not two outcomes. Therefore, we have here n factorial divided by x, y, z, y3 if there are three outcomes. Then p power x d p power ry 1 minus pd minus pr. This is the generalized formula. You can see an example here. Let's see an example of multinomial. You will understand it better. We'll go back again, try to understand this formula. What is multinomial distribution? You do an experiment, you get outcome. This outcome, if it is fixed to 2, that is binomial distribution. Okay, binomial distribution. But if this outcome is not fixed to 2, it means it is becoming a random variable. No, what is definition of random variable? When we discussed it, you do an experiment, you get lot of outcomes. Those outcomes are random. In that case, we call that variable which is storing that outcomes as random variable. Here it is becoming a random variable. So this problem, if you are randomly choosing 8 people from an audience that contains 50% Democrats, 30% Republicans, and 20% Green Party. Okay, randomly choosing 8 people, that audience, from an audience, total population is given to us, which out of which 50% are Democrats and 30 here are Republicans and 20 are Green Party. Okay, what is the probability of choosing exactly 4 Democrats, 3 Republicans, and 1 Green Party? What is the probability of choosing exactly 4, 3, and 1? So this is what P d equal to 4, R equal to 3, G equal to 1. So total is 8 factorial, n factorial by those 3 factorials, that is 4, 3, 1 factorials into. Now, what is this 0.5, 0.3, 0.2? Because what is, now tell how I got this 0.5, 0.3, and 0.2. Out of 100 people, what is the probability of getting a Democrat? That is 50 by 100, 1 by 2. Sorry, it is, yes, 1 by 2. Getting Democrat is 1 by 2. 50 by 100, 1 by 2. Okay, what is the probability of getting Republican? From these 100 people, if you choose one person, what is the probability of getting a Republican? Republican are 30 in 100. So 30 by 100. Okay, 0.3, then 0.2. That's what we have multiplied together. So we get this. Okay, right? So this is about multinomial. If you see this 3 again, in binomial distribution, if it has fixed number of observations, why I am talking about fixed always? Because these are discrete. These are discrete probability distribution functions. In this, we have finite number of observations. So fixed, and it's a binary random variable. So this is about multinomial distribution. And the next one is Poisson distribution, which is a discrete distribution function. What is this Poisson distribution? Again, it's a discrete only, so we have finite only here. Let's see what is the difference from the previous ones. Poisson distribution is for counts. Even if events happen at a constant rate over time, it gives the probability of X number of events occurring in time. I'll just make it simple. You do experiment. You are doing experiment. Again, here it's saying event or experiment. So experiments you do. Okay. So you repeat that one at given repeat. You are repeatedly doing that experiment. You are repeatedly doing that experiment. Now, in that, maybe you have started doing from 6 p.m. You have started doing the experiment till 7 p.m. Okay. Now, this is being done recurrently. It is being repeated. Right. So, given a time 6:35. Okay. Or given a time 6:35 to 6:45. During this time period, you take observations during that time period and you analyze the data. Okay, if events happen at a constant rate over time, so 6 to 7 it is happening, the Poisson distribution gives the probability of X number of events occurring in time t. Okay, so like this, we will see examples. Number of customers arriving in 20 minutes. Number of strikes per year in India. So we're talking about time. We're talking about a time stamp. Events happen recurrently, but we are asking, see, number of customers arriving in 20 minutes means Customers are arriving continuously. In that, how many are coming in 20 minutes? You see this one, strikes per year in India. Every year strikes happen. I am asking average number of strikes or per year in India, how many strikes are happening. Okay, that way we use Poisson distribution. So it is represented with this formula P of x. Why P of x? Because it's a discrete probability function. Okay, that's why P of x equal to lambda power x into e power minus lambda by x factorial. Okay, so probability of x is given by lambda. Probability of this x is given by lambda. Lambda mean number of events in unit. E is fixed 2.17. X is number of events per unit. Let's see an example for this. Let's try to understand Poisson distribution with an example. It is linked with time. So any problem, if it is given as find out the probability of getting a particular outcome, then you have to, and it is given with respect to time, you should focus on Poisson probability distribution. So see this example. Customers arrive at a rate of 72 per hour. Okay. So per hour, 72 customers are coming. What is the probability of 4 customers arriving in first 3 minutes? What is the probability of 4 customers arriving in 3 minutes? Okay. So it's linked with the time. They are talking about hour, minutes, right? So the mean is given as 72. If you see this, lambda is your mean number of events in a unit, that is 72 on an average. E value, you know, x value, number of events per unit, that is here they're asking about this arriving in 3 minutes. So let's see how you solve. So 72 per hour means 1.2 per minute. Okay, so 3.6 per 3 minute interval. For 3 minutes, 3.6 are coming. So your lambda becomes 3.6. So 3.6 power 4 e power minus 3.6 by 4 factorial 0.1912. So the probability of 4 customers coming in first 3 minutes is 19% or 0.19, very low. Okay, so these 4 are the discrete probability distribution functions, right? If anything is linked, now you may ask me, where are all these distribution functions used? Okay, we have seen different distribution functions like binomial, Bernoulli, multinomial, and Poisson. Where are these distribution functions used? In data science, you have lot of queries. See, the job of data scientist is to do find out insights from the data. I have to find out insights from the data. So sometimes you should understand the how the data is distributed, how the data set which is given to me is distributed. Okay, so and data you have already with you. There are advantages of studying how the data is distributed. There are some benefits of studying how the data is distributed. This is second case. Now you have a lot of queries to find out. You have a lot of queries. You want to draw insights. You want to check what is the 1 month transaction, how much percentage of what we say shopping has been done by an employee. Average shopping has been done by an employee in last 1 year, in last 1 month. I have to derive from this data which is given to me. For doing that, I have to understand how the data is distributed, and based on the query, you have to transform that data into particular distribution and then find out its response. Okay, so this is used at a higher level where data scientists, there are a lot of, they do logical work where they try to understand the hidden patterns in the data and try to identify the data distribution. So for there, we'll be using these distribution probability distributions. Now let's see few of the continuous probability distributions. Continuous probability distributions. Okay, so in that one is uniform probability distribution. Uniform, this is one very popular probability distribution which is used. Let's see this example to understand what is uniform probability distribution. Okay, consider a random variable x representing the flight time of an aeroplane traveling from Chicago to New York. Okay, x is a random variable. It represents the flight time of an aeroplane traveling from Chicago to New York. It's a random one. Sometimes it goes in no 2 hours. Sometimes it goes in 2 hours 10 minutes. Sometimes it goes in 1 hour 55 minutes. That's why we say it's a random variable. We are saying it's a random variable. What is it representing? It is representing the time taken by a flight to go from Chicago to New York. From Chicago to New York. So see, so under normal conditions, flight time is between 120 to 140 minutes. Okay, because flight time can be any value between 120 and 140, x is a continuous random variable. It's a because it can be anything. It's a random variable, that's okay. But since it is changing always, I can get 121 minutes, 129 minutes, 140 minutes, 136 minutes. It is changing. Or 121 minutes, 33 seconds. It may happen this way also. It can land, the time taken might be in seconds as well. Right? So it is a continuous random variable. Now, with every 1 minute interval being equally likely, the random variable x is said to be have uniform probability distribution. For every 1 minute, see, it is okay. It is, I will say, you know about discrete. Discrete says if this 10 MCQ questions, it is between 1 to 0, 1 to 10. Continuous says if it is something between weight, it is something between 0 to 10, but I have infinite number 0, 0.01, 1.02, 9.86. Like this, I have so many values in between. Okay, in these continuous, in this range of continuous infinite number of values, I am taking some 0 to 1. Okay, I am taking equal, I am making it partitions. I am making it partitions inside it. Okay, so with every 1 minute interval, with every 1 minute interval 0 to 1, being equally likely, the random variable x is said to have uniform probability distribution. It means this variable x, that is the time 120 to 140. Okay, if you take one interval time 120 to 121 minutes, this range if you take, okay, so always the flight, if it is coming between this interval, assume flights are having timings. So I'll take example 120, 120.05, 120.56 seconds, 121, 121.36 seconds, 121.57 seconds, and so on. It is there. Now, if I take this range of 1 minute, in this if these two times are always equally likely, means if these two times are always appearing, this is becoming something like a discrete, right? This range only I'm talking about, this 1 minute, it is becoming something like a discrete. So when there is such kind of an variable x, in which in taking in 1 minute interval time, if the every 1 minute interval being likely equally likely, then we say that random variable x has uniform probability distribution. So it is given something like this: f of x equal 1 by 20 for 120 to 140, or else 0 elsewhere else. So see, f of x equal to 1 by b minus a. How I got this b minus a? That is a less than or equal to x less than or equal to b. I said 120 less than or equal to x less than or equal to 140. So this will be f of x will become 1 by 20. 1 by 20. Okay, so for the flight time, the random variable a is 120, b is 140. That's why we got this as 1 by 20 for f of x. What is 1 by 20? Is the probability. Probability of a flight coming in between this range is 1 by 20. Okay, right. So if you can see, the shaded area indicates the probability that the flight will arrive in the interval 120 to 140. This is what uniformly distributed. The density, it is not something like this. Okay, and also it is not something this fashion. Maybe we have seen in other distributions that something is like this. This also we have seen distributions. Okay, though it is discrete, there are some changes, and the continuous something like this. But uniform probability, you see, we have a fixed time range like this: 1 by 20. A flight coming at 120 is 1 by 20, coming at 125 is 120, coming at 128 is 120. Always the probability is 1 by 20. Okay, so suppose somebody asks you what is the probability that the arrival time be between 120 and 130. Okay, the arrival time is between 120 and 130 if they ask. Generally, I know it is coming between 120 and 140. In that, if somebody asks, what is the probability that the flight will arrive between 120 and 130? So you have to just multiply. So area, that area is 10 into 1 by 20. So it is 0.5. So it is 0.5. So the probability of a flight arriving between 120 to 130 is 0.5. It's very, very simple. It's just 1 by 2. By seeing this, you should say, if I ask you what is the probability of a flight arriving in 125 less than x less than 135. Okay, in such case also it is same. The area is 10. So answer will be 0.5. Next one, normal probability distribution. Very, very popular one. It is very widely used. Always we say, even if you remember, when we talk about central limit theorem, in statistics, okay, very powerful algorithm in statistics, central limit theorem. Here we said, given a population's data, which is normally distributed, which is normally distributed. Then you draw some random samples S1 to Sn. Each you find out mean of those samples. Those means form another sample. Then you find the mean of sample mean. So that's about central limit theorem. But there we said that given the population's data which is normally distributed. Okay, what is this normal distribution here? So the normal distribution is by far the most important distribution for continuous random variables. It is widely in making statistical inferences in both natural and social sciences. So it is widely used. Heights of people, test scores, scientific measures. Lot of people. If somebody is faculty, we do grading of students. We do normal distribution like S grade, A grade, B, C, D, E, and F grade. So here we give 2, then here it is something, maybe this is 2. If this is 4, this is 4. Then if this is 8 and this is 8, that way we distribute it normally. Okay, that's why it is given test scores, right? So normal distribution is followed widely in lot of applications. Let's try to understand this in detail. Even in data science, we'll be always talking about data is whether it is normally distributed or not. Normal probability distribution. So the normal distribution is given with this formula 1 by standard deviation square root of 2 pi e power minus x minus mu whole square by 2 sigma square, that is variance. You know about mu, that is mean, x is the random variable, and sigma is the standard variance. This is standard deviation, pi value I know, e value I know. Okay, let's see example, try to understand this detail. What is normal distribution? Okay, so few characteristics of normal distribution. The distribution is symmetric and bell shaped. It is symmetric and bell shaped. Bell curve. We say that's why we say bell curve. Why is a bell curve? Because it is normal. It means what is increasing this side, it's also same thing in this side. Perfectly designed. Okay, it is symmetric. That's why it's a symmetric. See, whatever is there here, same thing is there this side. Symmetric and bell shaped. Second one, the entire family of normal probability distribution is defined by its mean and standard deviation. So its mean always in the center and standard deviation is this. The variance, no, standard deviation, how far they are difference to each other. The highest point on the normal curve is at the mean, which is also the median and mode. If the data is normally distributed, its mean, median, mode are all same. And the highest peak point is your mean. The highest peak point is your mean of this data, which is also your median and mode. Next one, the mean can be any numerical value, negative, 0 or positive. Mean can be any negative value. The average value can be any negative, because we are not plotting in any x or y axis. We are just plotting in one direction. So it can be anything, 0 or no. If you see for this, it is 0. For this 20, it is minus 10. For this curve, it is minus 10. Right? So it can be any value, mean distribution. This is one very important formula you have to remember. Then The standard deviation determines the width of the curve. Standard deviation defines the width of the curve. Larger values result in wider, flatter curves. Larger values result in wider and flatter. See here in this example, if you see this distribution, the green color one, its deviation is large because it is varying from here till here. Whereas for the smaller one, blue color one, you see the variance standard deviation is very, very low. So if by the help of standard deviation, you can guess the width of the curve. Probabilities for the normal random variable are given area under the curve. How we give the probability, how we use this normal probability distribution in problem solving is that we find out the area under the curve. So they ask you this area, if they ask you this area under the curve, so based on that we divide. This is, see, exactly half. So this is 0.5, this is 0.5. If this I say this is 0.2, if I say last one, if I say this small one, it is 0.1, this is 0.2. So this range is 0.3, maybe this is 0.4, and the total is 0.5. Okay, so probabilities are given as areas under curve. The total area on the curve is 1, 0.5 on the left and 0.5 on the right. Next, the standard normal distribution with the special property, that is mean is 0 and standard deviation is 1. Okay, so in normal distribution we have something called standard normal distribution. What is the standard normal distribution? If its mean is 0 and if its variance is 1, standard deviation is 1, then we call that particular distribution as standard normal distribution. So we use the letter Z to indicate standard normal random variable. We say it as Z, standard normal distribution. See, the mean is 0, the average value this is 0, and the variance or standard deviation is 1. This is a special case of normal distribution. So some example questions. So how do you find out the probability? Probability that z less than 1 is the area under the curve to left to 1. So if the question is probability of z indicates standard normal distribution. Z less than or equal to 1. What is this? Nothing but the area, which is area left to 1. This side. This full is your area under the curve of z less than or equal to 1. If z is greater than or equal to 1, this will be the region. So only you have to find out this region, you tell its probability. You can tell its probability. Okay. So yes, so this is about different kinds of probability distributions. What we have seen, we have studied about discrete probability distributions like binomial, Bernoulli, and multinomial and Poisson probability distributions. Whereas in continuous, we have studied about uniform and normal distributions. A special case of that is your standard normal distribution we have seen. So this is the reference book for probability and statistics. So most of the content what we have discussed here, it is from this book, Probability and Statistics.